Okay, Bismillahirrahmanirrahim. Salatu wassalamu ala asyrafil anbiya'i wal mursalin. Right. So last time we learned about kind of map, where kind of map can be used to also to represent binary values of input variables, and okay, from the kind of map we can also minimize or simplify the expression. Okay, so based on the rules given that we have learned previous lab. Um, right. So once you have a simplified, okay. So once you have a simplified version of functions, okay. So regardless that if it's from Kanomap or um, uh, Boolean algebra, okay. So the next step would be drawing the logic gates. So what is gate? So a gate is an electronic device that produces a result based on two or more input values. So forgot. Okay, logic gate. Alright. So a gate is an electronic device that produces a result based on two or more input values. So means that the the gate, okay, can have maybe one input values, or maybe have two input values, or maybe have more than two input values. Okay, so but in reality, gates consist of 1 to 6 transistors, but digital designers think of them as a single unit. So integrated circuit or IC, okay, contain collections of gates suited to a particular purpose. Okay, so what's the meaning of the particular purpose? You will see after this a combinational logic that is that serve a certain purpose of operation. Okay, so there are three simple gates, AND, OR, and NOT gates. Okay, so for AND operation, okay, we use this symbol, okay, which contain two input, okay, and one output. And then for OR gate, okay, operation, so at least one bit must be one input must have bit 1, then the output will get 1. So the logic gate, okay, symbol that must be used is like this. Okay, so with the 2 input and 1 output. And then we have a NOT gate that have 1 input and 1 output. So they correspond directly to their respective Boolean operation. Okay, so if operation AND means X, Y. If operation OR, it's X plus Y. And then if it's operation not X, means X bar. Okay, so each of these operation have their own truth table. So another very useful gate is the exclusive or in simplified form is XOR gate. So the output of the XOR operation is true only when the values of the inputs differ. Okay, in this case, X or Y, okay, with a symbol plus and a circle, show the truth table. As you can see in the truth table, okay, the output here, okay, will only one when input has different values. Okay, for input X is 0, input Y is 1, then the output will become 1. Or if the input X is 1, then the output Y is 0, then the output will become 1. So you can see the example on the previous lab where when you write A prime B plus A B prime, right? So it's like this. if you extract the SOP function, you will get x bar y, x, y bar. So when you combine, you will get x bar y plus x y bar. So basically, if you simplify it, you will get x and then x or y. Okay, so the symbol here is like this, and or, and then there's another extra here. Okay, another extra line to show that this is XOR. Okay, so note the special symbol for the XOR operation. Right. Another logic gates. Okay, another logic gates is none and nor. Okay, so none and nor is a combination of not. Okay, plus n. And then nor is the combination of not and or. Okay, thus they come the words none and nor. So these two none and nor are two very important gates. Their symbols and truth tables are shown at the right. So okay, so remember gate n first. Okay, remember gate n. So xy is, if you are xy, if you end the xy, so you will get 0, 0, 0, 1. But okay, if you not it, so xy not, so it become a none. Okay, x none y. Okay, so x none y. So if we not it, okay, if you inverse it, you will get 1, 1, 1, 0. Okay, so that's what's come x, y full bar. Okay, and then it was also equivalent if we are using a De Morgan theorem. Okay, so use a De Morgan theorem, x, y full bar. Okay, so to remove the full bar. So if we want to remove the full bar, here n become or, and x and y, then we will have a small bar. So it was equivalent to the truth table here. And then how do we want to draw it? So if you see it here, x bar or y bar. So means that we not first. Okay, we not first. Then we put an OR gate. Then we will get x bar or y bar, which is equivalent to xy full bar. Okay, so this is NAND gate. So you cannot say that this is a NAND gate. Okay, although the symbol use OR gate. Okay, because of the truth table is the same. The truth table is the same. Right. For the next one, no x nor y. So let's say x plus y. Okay, so x plus y is 0, 1, 1, 1. So if we not, okay, we want to put a NOR gate. Okay, so NOR means we OR first, then we not after that. So this is a full bar. So what's become is 1, 0, 0, 0. Okay, so this is a NOR gate. Okay, so the symbol for a NOR gate, like a normal one or a standard one, is we put an OR here and then a NOT in front of it. So we will get x or y and a full bar. But we can also represent using a gate n. So you have to use a De Morgan theorem to separate the full bar here. So since this is OR gate, so it become n. Okay, so it become n. And then this is x bar, okay, and y bar. Okay, so to represent the gate, okay, to represent this gate, x bar and y bar, So means that X, we bar it, and then Y also, we also inverse it. Then we put an AND gate there. So you will get the same truth table. Okay. Why are they using a NAND and NOR gate? NAND and NOR gate are known as universal gate because they are inexpensive to manufacture, and any Boolean function can be constructed using only NAND or NOR gate only. Okay, so okay, example, we want to use a NAND gate, okay, to represent operation NOT. Okay, to represent operation NOT. So NOT is only one input, and then input X. But remember, if we want to use a NAND gate, they must have two input. So to make two input, they will split one input here to become two input. And then when they come across the NAND gate, okay, NOT, and then with and with the NOT gate means the NAND gate, we can get a NOT operation. Okay, so you can test this. You can test this by using a truth table. Okay, using a truth table, 0, 0, 0, 1, okay, 1, 0, 1, 1. So let's say we want to use a NAND gate, right? So X dot X. So 0, 0, 0, 1. See? So 0, 0, 0, 1. And then we want to you want to NOT, okay, put a NOT gate, right? So to put a NOT gate, okay, so we put X dot X full bar. So it will become 1, 1, 1, 0, like that. Okay, so basically it can be the same. But if you can see it here, this is not a NOT operation, right? Okay, so to follow the NOT operation, okay, I'll stop this and okay, let me show this one. This one. Okay. Okay, previously you have download lab 4, right? So when you download the lab 4, okay, so this is the representation. Okay, so this is the representation of the NAND and NOT gate. NAND and NOT gate. Okay, so NAND and NOT gate. So this is a NAND and NOT gate. And then so to represent a NAND, okay, we use the same input here. So sorry, so this is a NOT operation. Okay, so this is a NOT operation. So this is a NOT operation. Yes, yes, yes. So this is a NOT operation of a NAND gate. Okay, of a NAND gate. So in this case, if we write the let's use a pin lah. Let's use the pin. Maybe you cannot see it. Let me make it one pages. Yeah, like this, right? Okay, hope you can see it. Okay. Macam ni. Okay. So this is a NAND gate. Okay, so since this is an A, okay, if we put a NAND gate, it will become A bar, right? So here means that A is 0, 0, and then 1, 1. Okay, so 0, 0, and 1, 1. It cannot be different, It cannot be different. So if we A dot A bar, okay, so if you put A dot A bar, so here means that 0 and 0, and then we bar it, we will get 1. And then 1 and 1, we bar it, you will get 0. So this is your truth table using a NAND gate. Okay, so based on the truth table. Okay, next is for AND gate. Okay, for AND gate, we use two NAND gate. Okay, we use two NAND gate, and you will get the same operation of AND gate. So here, let's say we want to use a NAND gate, okay, to represent AND. Okay, so we have A, B here. Okay, so what we have here is A, B. So the product is A, B prime, right? So to get A and B, okay, so we NAND again. Okay, you NAND again. So when you NAND again, actually you would remove the full bar here. Okay, so means that you put another bar. Okay, when you put a NAND, actually you are adding a NOT operation. So previously this NAND gate has A, B full bar. So now when we put another NAND gate which become a NOT gate, so it become a double bar. So double bar means A, B. So we remove the bar. So that's how we get an AND gate. What about OR gate? Okay, so to get OR gate, we NAND each of the input. So A NAND, okay, when A comes through the logic NAND, so it will become A prime, right? Because this is NAND gate can become a NOT gate. And then also with the input B, if they comes across the NAND gate, then the output will become B prime. And then remember we want to add. Okay, so we want to add we want to become OR gate, right? So when we add another NAND gate here, okay, when we add a NAND gate here, so we will NAND it. Okay, so we will NAND it together. Okay, so A prime or end with B prime, and then because we have a NOT there, so we have a full bar. So once we have this full bar here, okay, so once we have the full bar, so first is that A, and then okay, so now you will get A bar, and then B is B prime. Okay, B prime. And then now when we NAND here, so A prime end with B prime, and then we NOT it using the De Morgan theorem. Use the De Morgan theorem. Okay, and here becomes OR, and then A and B here becomes double bar, which is equal to A or B. Now we can get A or B operation. Okay, what about NOR operation? Means NAND gate can represent a NOR gate. Okay, NAND gate can represent a NOR gate. So first is that so we get an A. Okay, input A, and then we okay, input A, we NAND it first. Okay, we NAND it first, then you will get A bar, and then B NAND it, and then we will get B bar. So combine together, okay, we will have previously we have A prime, B prime, and then a full bar. Remember? Okay, now Okay, so now we have this, or what we can say equal to A plus B. Okay, so now if we want to have a NOR gate, okay, so A nor B, like, right? So NOR gate means that the function is A plus B and then with a full bar, right? So to add a full bar here for this expression A plus B, then we add another NOT gate. Okay, so we can add another NOT gate, or what I mean is we can add operation NOT. So add another NAND gate here, and then you will get A plus B prime, or A plus B full bar, like that. Okay, so it's also the same with the gate NOT. Gate NOT, no, gate NOT. Right. So to represent NOT gate, okay, to represent NOT gate, so NOR gate can also represent the operation NOT. Using a single NOR gate, then you will have a NOT operation. Okay, so based on the truth table. Okay, so based on the truth table, okay, so not A. Okay, not A. So for truth table not A, we use two input. So one is 0, 0, and then one is 1, 1. And then A plus A and then full bar. So 0 plus 0 is 0, and then bar it, you will get 1. And then 1 or 1, and then we inverse it or we NOT it, so you will get 0. So basically, a NOR gate here can represent NOT operation. Okay, so what about AND? Okay, AND operation. So for AND operation, it's the opposite of the NAND gate here. See? So for a NAND gate, you will add, okay, first we NOT it and then we add another NAND gate, so to get an AND operation. Okay, but for OR gate, okay, so we need to NOT it, okay, you need to inverse each of these gate to become a NOT gate, so A prime and B prime, and then add another NAND gate. Okay, so for OR gate, we need 3 NAND gates, and then for AND gate, you will need 2 NAND gates, right? So now, for the NOR gate here, if you are using a NOR gate to represent AND operation, so it's the opposite with the NAND. So instead, okay, each of these input A will need to be inverse with a NOT gate. So to inverse with a NOT gate, we use one NOR gate for each input. Okay, to get A prime and then B prime here. And then we combine both. Okay, we combine both input using a NOR gate again. Then you will get A prime or B prime. Okay, A prime or B prime. And then, I forgot. Okay. It should be, the operation should be like this. Okay. Let's say this is A, and then we have a NOR gate, and then you will have A prime, and then B here. Oh, Allah. Okay. And then we have B prime like this, right? And then you combine it, okay, you NOR it again. Okay, you NOR it again. So here, sorry, this is a B prime, right? So A prime or B prime and then another full bar here. So remember the De Morgan's theorem, okay? Or becomes N, and then A double prime, B double prime is equal to A and B. Okay, so it's the opposite with the NAND gate. So this time we need 3 NOR gates. What about OR? Okay, so what about OR? A NOR sorry. A or B, okay, A or B to represent using a NOR gate. So we have A and then we have B. Okay, we know it first. Okay, we know it first means A plus B and then put a NOT gate. And then we just need to remove this full bar only. So to remove the full bar, we need to put another bar. So to put another bar, just add another NOR gate. Then you will have A plus B full bar equivalent to A or B. Okay, so that's the opposite. Okay, and also the same concept to represent none using a NOR gate. Okay, so basically they are the same. See? They are the same expression to represent the NOR gates. Okay, so that is about the universal gate. Madam, can I ask question? Is there any difference between bullet black and bullet white? Bullet black and bullet white. Yes. Remember when I draw the bullet, right? Hold on. Okay. So let's say a bullet white here represent like this. Okay, represent a knot. Okay, a bullet white there represent a knot, but a bullet black, for example, like I draw yesterday. Remember when I draw it like this, and then I put a bullet black there, right? It's like you are tapping. Okay, you want to connect to that circuit. Okay, so you want to connect to that circuit, so I put a tap there and to represent, I put a bullet there to represent that I was tapping the circuit. So I was connecting using this A circuit here before it goes to the NOT gate, and then pull another circuit. Okay, so to connect with other gates. For example, here B, and then I would like to end it like this. Okay, so what would I get is AB. Okay, so that's the difference, right? So to represent the tapping, or means that you want to take out, you want to extend the circuit, then use the black bullet. And then if you want to represent a NOT gate, then use a white bullet. Okay, you can also, okay, you don't have to put a triangle here to represent a NOT gate. Okay, because sometimes, okay, we can just represent it like this, just like this, and then you want to put an N here. Okay, so one is a NOT gate, and then another one is not a NOT gate. See? Okay, so let's say this is A, this is B. So one has a NOT symbol, and then another one doesn't have, right? So the output will become A prime B, just like that. But why am I using this? It's because sometimes the NOT gate will be repeatedly used or combined with other gates. So I will put a single NOT there, and then in case there's a repetitive usage, then I'll just tap it. Okay, just tap with the black bullet and then drag it to the other combination. Okay. So let's continue. I hope you can understand my explanation. Okay, so the logic NAND and NOR gate is you need to understand how to construct for each of the basic operation, NOT and OR, and then the other opposite. Okay. Now, gates can have multiple inputs and more than one output. Okay, so it can be one input in like a NOT gate, and then it can be two input like AND gate or OR gate. Okay, so but between this AND gate, OR gate, NOR, NAND, okay, sometimes, okay, sometimes we can have more than two inputs. Okay, so but for a NAND gate, it would be a little bit tricky actually. Okay, so how do we want to represent? Okay, how do we want to represent a NAND gate for 3 input? Quite hard actually. So what you can do is that first you NAND 2 input, okay, and then NAND again. Then you will know how to write the truth table. You know how to write the truth table. Okay. Right. So as you can see here, okay, since practical things, the practical gates can say that they can get multiple input. Okay. So means when you draw your logic gates, you can just combine the multiple inputs here. Okay, so based on the variables or the combinations needed. Okay, and then also there are certain conditions that you can get 2 output. Okay, 2 output which will be explained later on. Right. The main thing to remember is that combinations of gates implement Boolean functions. So the circuit below implements the Boolean function. So previously we have the functions x plus y bar z. Okay, so to represent the, let's say this is already simplified. Okay, so this is already simplified. As you can see, there's no more similarities of variables that we can simplify anymore. So we can just draw the circuit. So x plus y bar z. So first is that we draw the line or the input. Okay, so don't simply put, let's say we have x plus y bar and then you put a y bar there. No, that's not the style. So it usually in the normal state x, y, z. Okay, so x, y, z. So your input need to be labeled as what the functions indicate. So x and then y and then z. Okay, and then we have y bar z. So y bar z. So y needs to be inverse. Okay, inverse. Put a NOT gate there, and then we here we will get y bar, and then we can AND it together with the input z. You will get y bar z, and then OR it with x. So means that you will drag the x until you will reach the OR gate here. So thus you will have the final simplified expression x plus y bar z. Okay. Let me put it here. All right. Okay. So if we have designed a circuit that implements the function x plus y bar z, for example, that's an example. So this circuit is an example of a combinational logic circuit. Okay, so why do we call a combinational logic circuit is that when we combine this together like this circuit, as you can see, so each time there's a input value comes through the circuit, we will always have the result instantly. Okay, you will have the result instantly. See here, the keyword is instant. Okay, combinational logic circuit will produce a specified output almost at the instant when input values are applied. Okay, but in a later section, we will explore circuits where this is not the case. Okay, so in this case, as long as there's electricity powered to the logic circuits, and then there's an input coming in and coming out. Okay, if there's an input coming in, then the output will be produced instantly. All right, sorry. Okay. Okay. One of the simplest example is the half adder, which find the sum of 2 bits. So as we see, the sum can be found using the XOR operation and the carry using the AND operation. This one, So how do we get the half adder? Okay, how do we get the half adder? So what is half adder? Okay, so what is half adder? Let's say we have two inputs. We have two inputs, X, Y. So we want to add. This time, we want to X plus Y. So to add X plus Y, for your truth table, you will write it like this. And then we sum and then carry. Okay. So this is like two different outputs. This is a two different outputs. So 0, 0, 0, 1, 1, 0, 1, 1. Okay. Sum is the result of the addition. Carry here means that if the sum contain 2 bits, then the most significant bit will be on the carry bit. Right? So when we sum 0 plus 0, plus here means add. 0 at 0, 0, 0 plus 0, 1. 1 plus 0 is 1. And then 1 plus 1 is 2. So 2 here, okay, in binary is 1, 0. So 0 here would become the sum. And then carry will become 1. The rest is 0 because they don't have carry bit. Okay, so this is what happened when we do a adding. Okay, we add between 2 bits. Okay, between 2 bits. So the output will be sum and also carry. So to get a sum, use SOP. Okay, use SOP. Here is X bar Y. And then this one is X Y bar. Whereas for the carry bit is X Y. So your function for sum, just write it. Sum is equal to X bar Y plus X Y bar. And then carry is equal to X Y. So how do we draw it? So to draw it, they are the same input. They are the same input, So X Y just like this, and then since X bar Y plus X Y bar, we can also represent it using XOR. X or Y. So you can put it like this. Macam ni. Put it like this. And then add an X all there. So X or Y, okay, is equal to sum. Okay, so this is your sum. Right, what about carry? So for carry bit, okay, for carry bit, I will drag my Y here. And then I will put a black bullet there for my X. And then put a pipe and then drag it and then put an N here. And then what would I get is my X, Y, which is my carry bit. Okay, so this is half adder. Okay, this is what we call as half adder. So why is it half adder? Imagine you have 8 bits, Imagine you have 8 bits. For example, what number, or whatever. 1, 0, 0, 1, 1, 1, 0, 0, like that. And then you want to add with another bit 0, 1, 0, 0, 1, 1, 0, 0, just like this. Okay, so for the first column here, okay, we just add it as usual. And then if there is a carry bit, then we carry it forward. So in this case, this is what we call half adder. Okay, half adder. But what about the bits that is in the middle? So you would expect there's a carry bit coming from the previous operation. Okay, so the carry in and then there's a carry out. Okay, so there is a carry in and there is a carry out. So look back at the slide. We can change our half adder into a full adder by including gates for processing the carry bits. So here, alamak, I forgot to open it. Hold on. Hold on. Okay, while waiting. Okay, so now this is the half adder. Now full adder. Remember the position. So for the full adder, there are 2 input bits and then 1 input carry. Here. Okay. So now full adder. Okay, full adder. So for bits that is in the middle and until to the most significant bit until the end of it. Okay, so what we need is 1 carry in and then 1 carry out and then 2 input and the sum here. Okay, so the sum. So how do we represent it? Okay, so now let me draw back again. Okay, so go to the slide. Okay, go to the slide. Yeah, this one. Okay, let me draw it. Now, for x plus y with a carry in means the bit is in the middle, right? So your input would be h, x, y, and then carry in is I'll just write c in. I'll just write C in. Alamak, cannot see the text anymore. If you have a question, yeah. Okay, so now we have X, Y, and then C in, and then our output will become sum, and then carry out. Because we have 2 carry bits, right? One is carry in, and then one is carry out. So I would represent it as C is a carry, and then there's an in and also out. In is an input, out as output. And then, now because we have 3 inputs, even though C in is a carry bit, right? So it's still an input. Okay, so the combination is the same. So 0, 0, 0, 0, 0, 1, and then 0, 1, 0, then 0, 1, 1. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. Now, we add it together. Okay, we just add it as normal way. So 0 plus 0 plus 0 is 0. C out is 0 because no carry bits. And then 0 plus 0 plus 1 is 1. Carry out 0. And then this is also 1, 0. And then 1 plus 1 is 2. So 0 in sum. Carry bit is 1. And then 1 plus 0 is 1. Carry out 0. 1 plus 1. Again, 0. Carry out 1. And then 1 plus 1 again. So 0 sum. Carry out 1. And then 1 plus 1 plus 1 is 3. So if it's 3, sum is 1. Carry out is 1. Okay. So now we have the truth table, right? So you have the truth table. So we try to simplify it, or you can just draw the Kano map. Use the Kano map, So we use the Kano map. It's because of the slide doesn't have the explanation, but instead of, you can just download. Okay, just download the notes from lab 6. Maybe I forgot to upload it. Yes. I'll upload it later. Okay, I will upload later. Okay, now this is the drawing of the kind of map. So since we have 3 inputs, then we can we just draw it. Okay, so sum here. Okay, so this is a sum, then x, y. Okay, and then c in. So okay, so let's use this one. X, Y, C in. Okay. No. No. I want to make it longer. So this one is X, Y, and then C in. Then this one is correct. Okay. Because of the space. Okay, because of the space, not because of the way we want to answer. Okay, so this is sum. Okay, for sum 0, 0, 1. Okay, 0, 0, 0, 1, 1, 1, 1, 0. So x, y, 0, 0, 1. Okay, so 0, 0, 1 is here. And then 0, 1, 0 is here. And then here is 1, 0, 0. 1, 0, 0. And then 1, 1, 1. So 1, 1, 1. So this is your Kano map for sum. And then for C out, okay, using the same table, okay, using the same Kano map, okay. Okay, so this is 0, this is 1, 0, 0, 0, 1, 1, 1, 1, 0. Now, for the C out, okay, so 0, 1, 1, 0, 1, 1, and then 1, 0, 1, 1, 0, 1, and then 1, 1, 0, 1, 1, 0, and then 1, 1, 1. So this is the Kano map for C out. Okay, so how to simplify it? Okay. Don't look at the sum first. Don't look at the sum. Okay. Look at the C out first. Okay, look at the C out. As you can see, how many circle I can have it? You can tell me. Tell me now. You can tell me now. You can just guess. First circle, which one I can draw? Which first circle I can draw? Just tell me.
0, 1.
0, 1 dengan?
Dengan 1, 101.
0, 1 here dengan 1, 0, 1. No, take the adjacent one. Take the adjacent one. So, ambil yang ni. Take out. Take out this one. Okay. So, this is your first circle, right?
Yes.
Okay. So, what's the next circle? Try the next circle. So, what's the next circle?
1, 1, 1.
1, 0.
1, 1, 0, 1, 1, 1.
Betul. Correct. Okay. So, the green circle here is this. And then for the blue circle, for the blue circle, okay, the last bit here, where I can borrow. Where I can borrow.
At 1.
Okay. Okay, because the rule said that each of the circle have 1 bit. That is not redundant. So, this is valid. Okay, so this circle is valid. So, regardless, the bit here has been borrowed or has been used 3 times. It is still a valid circle. So, here you can simplify it. Okay, this one we write back again x bar y, and then this one is xy, and then this is xy bar, and then this is c in, and then this is c in bar. So for the red circle here between x bar y and then xy, so which gate or which variable that does not change, and that's the one that can stay in the expression. So which expression? Which expression? The rest can type. Okay, the rest can type. You can just type it. Which expression for the red color? For the red color. Find the one that doesn't.
X bar Y C in.
X bar Y C in. Okay, simplify it.
Y C in.
Yes, correct. Okay, what about the green color here? Green color, mana? What? Okay, here. Okay, so the green color?
X Y.
Correct. Okay, so the column doesn't vary because there's a changes there. Okay, what about the blue color?
X C in.
Okay, yes. X C in. Okay, so now we can combine. Okay, C out is equal to Y C in plus X C in plus X Y. Okay, so can I simplify it? No, you cannot. Okay, because the K map shows that that is the most simplified version. Okay, what about sum? What about sum? As you can see, we can only have one single circle, right? We have one single circle like that. So how to we write it into Boolean function. Okay, so for Boolean function for this one is okay. We will write it back. Okay, because it becomes X bar Y bar C in, and then take this one X bar Y C in bar. Betul. X bar Y C in bar, and then plus with this one X Y, and then C in, and then plus what's this? Okay, X Y bar, and then C in. Okay, so this is the expression that we have, and then okay, to get the to simplify it. Yes.
Bukan XYC in bar ke?
X yang mana?
Yang last kali.
X Y bar C in. Yang ni. X Y C in bar. Okay. The second last one.
Yeah.
Tak. Ini this one is C in. This one is C in. Kejap. This one is C in. This one is 111. So X Y C in, and then this one is X. This is X, and then this is Y bar. So this is X Y bar, and then this is C in bar. Ai mak kau. Okay. Yes. Correct. So this is C in bar. Yes, thank you. Okay, so correct. Okay, now betul So now we have X Y bar C in bar. Okay, now you pair it. You can still pair it. So here the similarities is only the X bar, right? So X bar, and then we factor it with Y bar C in plus Y C in bar. Okay, and then plus X Y C in plus Y bar C in bar. Okay, now for this expression Y bar C in and plus Y C in bar, it's very it can be simplified to become Y X or C in. Right? The one side is bar, the other side, the other term is not it's a not, meaning a normal one. And then this one is 0, this is 1, and then this is 1, this is 0. So we can say that this is an XOR operation. So X bar, okay, factor with Y plus C in. Okay, so now so how to represent it using okay, we use AB lah, yang ni pakai X pula. Okay, so now okay, so for the second one, okay, for the second one here, X, okay, Y C in and then Y C in bar. If you look at the truth table of, let's say this is A, B, no. Let's use X, Y, X, Y. If we use X or Y, actually, so 0, 0, 0, 1, 1, 0, 1, 1, this would become 0, 1, 1, 0. If you convert this to an expression of SOP, so this one will become X bar, Y bar. And then this one is X, Y, right? So this one is very similar to this expression, and this expression is very similar to that expression. Okay, but the only thing is that this is a bit zero. So, but in this case, we can say that, okay, it's the inverse of the XOR. We can say Y XOR C in full bar. Okay, so if you put a bar here, automatically you will get 1 back again, this one. Okay, so it's a very similar with this expression X bar, Y bar, and then X, Y. Okay, it's just that it is the opposite of the XOR. So the opposite means that we can just put a full bar. Okay, put a full bar there. So now we will get, hold on. Okay. Now we get here. So how do we simplify it? Okay. Okay. Let's A is equal to Y XOR C in. Okay. This is like representation. I'm just representing. Okay, I just want to use this expression Y XOR C in to a variable A. Okay, anything, any variable except that X, Y, and C in. Don't use that variable. So now we can say X bar A. Okay, because this is inside like this, right? So we can just remove the bracket. So it will become X dot A. This one. Okay, so X bar and with the expression Y or X, Y X or C in. So now we can just replace the Y X or C in with A. And then this one with this expression, okay, X and Y X or C in full bar. So we can just represent Y X or C in with A and then put a bar there. Okay, so now as you can see, this one is X bar A and then this one is X A bar. So we can say this is X XOR A. Okay, so replace A equal to Y XOR C in. You will get X XOR X XOR make a bracket. This one make a bracket, okay? Because they are a single item. We call it a single item. We treat it as a single item. So Y X or C in. Like that. Okay? So now, alamak, dalam ni tak. Okay, you need to draw on your own. Okay. So you need to draw. Can I extend it? Okay, now make it bigger. Okay. Now we have the expression, right? we have the expression x or and then y x or sorry, y x or c in and then x or with this expression. Okay, so and then the other, so here is our sum, right? This is our sum, and then go back to the C out. C out is y c in plus x c in xy. So C out is x y plus x c in plus y c in. Betul tak? Betul tak? Let me check again. Yes. Now we have 3 inputs. Okay, so one is x, one is y, and then one is c in. Okay, you have a c in there. And now you can you can draw the XOR. You can draw the XOR here. Okay. Okay, this one. Okay, and then XOR with X. So now this is your sum. Okay, but what about your C out? You just tap it lah. You can just tap it. Maybe I'm feeling lazy or maybe the space is not enough. So I'll just take it out and X C in. Okay, now X, Y. Okay, now we can just draw it like this. Okay. Okay, and then this is X, this is Y. Okay, so now this is X, this is Y. Do we have Y C in? Oh, yes, we have it. So now Y C in is together with this one. We end it. Okay, so don't forget to write Y C in. Okay, and then X C in. So X C in. So here is X C in. And then XY. Okay, so for XY, like this. Okay, so combine it together. Okay, combine it together, you will get C out. Okay, not so very tidy or neat, but if we draw it using like a multimedia logic, they can rearrange it for you actually. So sorry about this. So this is how you want to draw it. This is how you need to draw it. But this one looks different, right? As you can see, the carry in here comes out from another side. Okay, so they want to rearrange it like so that it will looks better actually. Okay, so this is the same. Actually, this is the same as the one that we have drawn before. All right. Okay, so next is decoders. Decoders are another important type of combinational circuit. Among other things, they are useful in selecting a memory location according a binary value placed on the address lines of a memory bus. So address decoders with n inputs can select any of not 2 times n. It is 2 power of n locations. Okay, 2 power of n locations. And then apply in CPU control, which is an advanced topic which will not be covered in this topic. Basically, the decoder will decode like address memory. Okay, we have an address, right? So using the cache memory method, okay, we want to pinpoint where is the location. So to pinpoint the location, there is a certain codes or combinational codes given as an input, and then the input will goes to the decoder. Then we can identify the address of the location. Okay, address. Sorry, the location of the memory. Okay, so that's the address. Okay, so this is what a 2 to 4 decoder looks like on the inside. Okay, so this is X and also Y. And then what's the truth table then? Let me show you. This is a question, so I need to show you the truth table first. You don't have to build up the truth table, but dah terus masuk multiplexer. Let me say the decoder. This one. This one, This one is a decoder. Okay, so how we derive the truth table? So actually, given a certain codes. Okay, so the input here is the code, and then the output here will only light as one. It's like a LED. It's like LED. As you can see on the truth table here, we have input A1 and A0. So for a code of 00, then only D0 will have bit 1. The rest will become 0. So it's like a path that is going out. Okay, the path that is going out. Okay, and then 0, 1 means that bit 1 from D1. And then 1, 0 is bit 1 on D2. And then 1, 1 is a bit 1 on D3. So that is how decoder works. Okay, it's like the line will be enabled. Okay, the line will be enabled. So in this case here, let's say, okay, so 0 and then 0. Okay, so if it's a 0 and 0, so it will go to the 0, 0 will go to the NOT gate. Okay, and then okay, here it will go here, and then this one, and then for this is for Y bar, and then for X here, X is 0. So for 0, they will go to the NOT gate here, and then go to this line. So this line will have like will be enabled like an LED. Okay, so there's a light there. So only this path will be enabled. So any path or any bits that comes through this will go out as the output. Like that. So let's say we have 0, 1. So remember? So 0, 0. Okay, so the decoder that comes out will be X bar, Y bar. This one is X, this is Y. Okay, and then for 0, 1, this will become X bar Y. Okay, so X bar Y will light up or will be enabled. So in this case, if X is equal to 0 and Y is equal to 1, so means that X bar Y, so which output line is enabled? So X0 will go through here. Okay, now we are in the middle of the decision. Okay, where do we go? We go down or we go next? Okay, so we can do, they will go both ways. They can go both ways, but they need another input. Here is Y. Y is equal to 1. So if Y is equal to 1, 1 will go here. Okay, and also will go here. So here we can see this is not complete, incomplete, incomplete. This one is complete. Then the circuit will be connected. So since we have these two input, okay, which is ANDed, so they will be connected. Then the LED will light up. So that is decoders. Okay, But the decoder doesn't have to be connected to the LED. I'm just telling the how do you want to see that how decoders works. Okay, so once we select the path, so that path will be connected. They will be connected. So the bits can go to that path. Okay, so that is the decoders. Did I forgot the name? Yes, name. Okay. So the name here, the name depends on the input, the number of input and outputs. For example, a decoder that has 3 input and a decoder that has 3 input. So automatically the output is 2 power of 3 inputs. So we can get 8 outputs. We will name it as 3 to 8 decoder. Okay, 3 to 8 decoder. So here, let's say the input is X and Y. Only 2 input, right? So 2 input. Okay, so output is 2 power of 2 inputs. Yet here you will get 4. So that's why the name of the decoder would be 2 to 4 decoder. So what if the input is 4? What if the input is 4? So what's the name of the decoder? What's the name of that decoder? Can you tell me? Guys?
Again, madam?
What is the name of a decoder that has, let me write, that has input is equal to 4?
16.
What's the name of the decoder that has input is 4? So find out the output. Yes. 4 to 16 because 2 power of 4 is 16. Yes, correct. All right. So you just need to know the output is only one line only. Sorry. The output has many lines. Okay, the output has many lines. So means that which one will be enabled. Means which one will be connected. Okay, which one will be connected. Okay, now next is multiplexer. So this multiplexer is what we call as selector. Okay, selector. So a multiplexer will operate as the opposite of the decoder. Remember, the decoder has many output. Okay, but multiplexer has many input. Okay, multiplexer has many input, and then we need to select from this many input. We need to select which input that will be connected to the output. Okay, maybe the I0, maybe I1 will be connected, or maybe I2 will be connected, or maybe I3 will be connected to the output. So which input is connected? Okay, so we need to select. That's why the name of multiplexer can also be selector. So don't get confused. If they ask you what is a selector, then you say multiplexer. Why is it called multiplexer? It's like a reflection. Plex means you are being reflexing. You are reflexing like an angle. Okay, like an angle. So multiplex means that we have many. Multi is many. Okay, plexer means like a connection. Okay, so we have a many connection, but we only select one. Okay, so maybe this one. Okay, so the others was not connected, or at one time this connection on, or maybe at one time this connection will get connected. Okay, so this is what we call as a multiplexer, like a piping. Okay, like a piping. How do you want to direct your circuit. How you want to direct your circuit. Okay, so the particular input chosen for output is determined by the value of the control line. Where is the control line? Another, we don't call it input, but basically it's the control line. Okay, so they will decide, they will determine which input will go out as the output. Okay, so which input line will be connected to the output there. So to be able to select among n input, so we will use log2 base n control lines are needed. Okay, are needed. So in this case, okay, in this case, tak lukis pula. Hold on. Where's the book? Multiplexer. Let me draw. This one. Okay, guys. Okay. So this is a 2-input multiplexer. So if we have 2-input multiplexer, then you only need one selector. So how do we calculate that? We use this one. Log n base 2. Okay, for the number of selector inputs. Okay, so for example, let me draw lah. We do the calculation. You need a calculator. This one you need a calculator. So let's say input is 2. So your selector, the important part is the selector. So how many selector we need for 2 input? So 2, okay, what do we call for the symbol? I forgot. So it's like log 2 base 2. Like this. Okay, log 2 base 2 is equal to 1. Okay, so log 2 base 2 is equal to 1. So for example, let's say another example is, let's say if we have 4. Okay, so if we have input 4, so your selector would be log 4 base 2 is equal to 2. Okay, so you need to use a calculator to get the log result. Okay, log 4 base 2, then you will get 2. So, and then the input must be in base 2 actually. So, usually input 8. Betul. Okay, input 8. So, how many selector that we need? So, log 8 base 2 is equal to 3. Okay, so basically all base 2 will be can be used as how many inputs to derive the multiplexer. Okay, so now in this figure, so let's say input line is 2 select line. So find out the power, 2 power of n. So from here we can get the number of select line. So 2 select line is equal to 2 power of 2 means 4 input line. If we have 4 select lines, means that 2 power of sorry, this one should be 16. Yes. I want to write 3 actually. This one should be 3. I want to write 3. Right, so 2 power of 3 is equal to 8 input lines. Okay, and then what is the truth table? How does it look like for the truth table for the multiplexer? Okay, so this is for 2 select input. Okay, from figure 6.4 here, we have 2 select input, right? So we have 2 select input, S0 and S1. So for S0 and S1 to become the select inputs, and then we will decide which data input or input line will go out. So we will label it as D0, D1, D2, D3. Okay, no A, B, C, D anymore. Not A, B, C, D anymore. Okay, so that's why we call it as a data line. Okay, data line. Okay, so based on the select input, 0, 0 means the binary 0. We will, the output is, we select line D0. And then for S0 and S1, okay, S0 and S1, we select input D1. And then 1, 0, for select input 1, 0. We will select input D2, and then for 1, 1, we would select D3. Okay. So that is how they how the multiplexer works. Now, okay, this one. So let's go to the circuit here. Right. So read the questions. This is what a 4-to-1 multiplexer. Even though it says 4-to-1, it's because of multiplexer always have one output. Okay, they always have one output. So 4 here is the 4 is the input. So if we have 4 input means 2 power of 2. So 2 select line. Okay, 2 select line. So I'm referring to the power there. And then, so now input is stays there. Input stays there. No, the value was not referred in the truth table. So what we refer on the truth table is the S1 and S2. S1 and S0. So now, if S0 is 1 and then S1 is 0. Okay, S0 is 1 and then S1 is 0. So what is the input transferred to the output? Okay, the position here looks different, right? But here, S0 and S1, you would see it like the position of the binary. So S1 and then S0. So write it like that. S0 is 1. S1 is 0. So here convert it to decimal. Convert it to decimal. Convert it to decimal. So here is 1. Okay, decimal. Decimal 1. So we refer back 1 here to the input that will be connected together. So I1. Okay, look at I1. So here you can see. Okay, so S1 is 0. So here, and then we can have this one, S1 bar, and then this one. Okay, they have options here. Okay, so they will go here. And then for S0 is 1. So S01 will go here, and then they will go here. And then okay, so which one will be connected? We look at the input there. So we have, we have two selectors that is connected together. This one, this one. So means that the bit here, okay, can be connected together. And, okay, so since they are connected together, then the input can come out as the output, like that. Okay, but what about the rest? Because this is an OR gate, right? This is an OR gate. Okay, so the rest is 0. The rest is 0. And then this is 0. But only this one is bit 1. So then the circuit is connected and the input can be transferred to the output. Okay, so that is multiplexer. Multiplexer is like a piping. They give you a path. Okay, so they give you a path from many sources. So you need to close up and only one input can come out as the output. So that's multiplexer. Okay, so and then that's combinational logic. Okay, so that's combinational logic. Why did I cover that? It's because of your midterm will come out. They will ask you about the theoretical. So what I'm teaching you is only a theoretical. Only on the half adder and the full adder. did I teach you about the logic circuit, right? It's because that's the easiest combinational logic that you can draw. Okay, as for the rest, you just need to know the theoretical implementation on how it works, how decoders work, how multiplexer works, right? Okay. Oh, ada notes. No. Right. So next. Now I'll go to the sequential circuit. Okay, so as the name implies, sequential logic circuits require a means by which events can be sequenced. So state changes are controlled by clock. Okay, are controlled by clock. So a clock is a special circuit that sends electrical pulses through a circuit. Okay, through a circuit. So the clocks produce electrical waveform such as on the figure below. So we have a low voltage. This is a low voltage. This is low. This is high voltage. Okay. So low voltage, high voltage. Okay, and then from the low voltage to high voltage, we have a rising edge. And then from high voltage to low voltage, we have falling edge. Okay, so the clock will produce this for rising edge and falling edge. So where does the clock comes out? When you buy your computers or your processors, your CPU has a certain parameter called hertz, gigahertz, right? Hertz here is the number of instruction, okay? The number of instruction divided by time. So means that how many instruction that can be solved or can be executed within 1 second. So that's the parameter of a CPU in a hertz. So by using hertz time here, so they create a clock. They create a clock to determine. Okay, so 1 clock. Okay, we call it as 1 clock. How do we determine 1 clock? 1, okay, low voltage, okay, rising edge, and then high voltage. Okay, high voltage. So this is what we call as 1 clock. 1 clock cycle. We call it as a 1 clock cycle. Okay, so 1 clock cycle. It depends on the speed of your laptop. Okay, it depends on the speed of your laptop. So the higher it is, meaning the faster the cycle. Okay, so the faster means much more shorter to execute. Okay, so that is the clock cycle. So there's why do we need to build up a logic gate that use a clock cycle? Okay, so state changes occur in sequential circuits only when the clock ticks. Okay, meaning 1 cycle and then the state will change during that time. Okay, so circuits that change state on the rising edge or falling edge of the clock pulse are called edge triggered. They are called edge triggered. And then level triggered circuits change state when the clock voltage reaches its highest or lowest level. So here, okay, so we call it as a edge triggered when the state change from 0 to 1. But if it's a level triggered circuit, we call this it means that the state change from 0 to 1 from here to here. This one. This is what we call as level edge. Okay. So, but usually for the sequential circuit, they use edge triggered. Okay, they use age triggered to determine the state. Okay, so to retain their state values, sequential circuits rely on feedback. Feedback in digital circuits occur when an output is looped back to the input. Based on this figure, the output here, okay, is looped back to the input. So it becomes a feedback. Okay, a feedback, they go back as the input. So a simple example of this concept is shown. If Q is 0, so it will always be 0. It will always be 0. And then if it is 1, it will always be 1. Why? It's because of the output become the input. Here, so let's say the output is 0. So the 0 will be feedback back again to 0 here. Okay, 0, 1, and then when we go back, it will become 0. So what about if Q is 1? If Q is 1, so 1 will be feedback. So 1, 0, 1. Like that. Right? So that's the concept of feedback. Okay, so the concept of feedback. So to retain their state values, sequential circuits rely on feedback. So the feedback in digital circuit is an output that is looped back to the input. So in this case, the example of feedback is the most basic sequential logic components, the SR flip-flop. So SR here stands for set or reset. Okay, so the output here will be feedback to the other gates, and then the other the other output will be feedback to the other gates. So this is a SR flip-flop. Right. So the behavior of an SR flip-flop is described by a characteristic table. Here, we have QT means the value of the output at time t. And then QT plus 1 is the value of Q after the next clock pulse. Okay. Meaning the next one. Okay, the next one what it should be. Okay, so for example, if S and R bit is 0, so it will retain the value of QT. So regardless of QT is cik ni nak lukis ni. Jap. Let me. This is SR. And then this is QT. We have a QT. And then we have QT plus 1. You have 0, 0, 0, 0. Okay, QT can be 0. And then QT can be 1 during this S and R is 0. And then 0, 1, this is 0. QT and this time is 0. And then 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. 1, 1, 1. Like that. Okay. And now, alamak, I need to follow the QT here. There. Okay. So, if S and R, okay, is 0, 0, set and reset is 0, so it will follow QT. It will follow QT means no change. So, QT plus 1 is 0. And then if QT is 1, it will become 1 because it follow QT. Okay, next. What if set is 0, reset is 1? So what does it mean, reset? Reset means we reset back again. Okay, so we reset to 0. So if QT is 0, it will become 0. But if QT is 1, we will reset to 0. Okay, so regardless of the QT, they will reset to 0. Okay, what about set 1, reset 0, and then if the QT is 0, we will set to 1. You will set to 1, and then if the set is 1, reset is 0. Oh, hold on, let me drink water. If QT is 1, so we will still set it to 1. Okay, and then what about set and reset is 1 and 1. Okay, once you have set 1, and then you put a reset 1, it will be contradicting. So this one would become undefined. Okay, undefined. It's because of we cannot have the same bit for set and resets because set and reset should be different. Okay, should be opposite. So this is for SR. Okay, SR flip-flop. As you can see, when the state of S and R is 0, 0, means that the QT doesn't change. You will see that it follow, or actually they are trying to build up a memory. This is a memory, means that they will retain the previous value. So it's no change. It said no change means they will retain the value. Okay. So oh, kat sini rupanya. Okay. Now, the SR flip-flop actually has 3 input. Okay, and then with the current QT. Okay, with the current QT. So, like I have explained it to you before. And then look at the last note there. Notice the 2 undefined values. When both S and R are 1, the SR flip-flop is unstable. So, that's why they said it is undefined. How do we say undefined? Is because of it depends on the speed. On the speed of the circuit between the S and R. So they cannot determine which bit will be coming out. Okay, from the S or maybe from the R. Okay, so the SR flip-flop can be modified to provide a stable state. Okay, we don't want the undefined anymore. They use JK flip-flop. Oh, tak ada pula. So, JK flip-flop follow the same as SR. Okay, follow the same as SR. They just add. Okay, they just add extra bit here. Okay, so to become JK. This one, this one is an extra one. This one is for extra bits. Extra gate for the SR. Okay, to set up the state for 1, 1. Okay, to set up the state for 1, 1 so that it will become Q bar T. So in this case, for JK, okay, if it's a JK, let me, okay, for a JK, so if it's a 1, 1, okay, 1, 1, and then QT is 0, they would invert, okay, they would invert the value, so this one would become 1, and then if the QT is 1, then the QT plus 1 would become 0. Okay, so that is for JK flip-flop. Okay, for another flip-flop is another modification of the SR flip-flop, the D flip-flop. Okay, so it's the fundamental circuit of the computer memory. So thus the name of D comes from data. Okay, so D flip-flops because they want to store they want to create a memory cell. Okay, they want to create a memory cell from the circuit. So usually they modified the SR flip-flop. Okay, so comes from here. Okay, so this is an SR flip-flop, and then an input from D. So one is okay, one is a normal one, and then another input have a NOT gate. Okay, so that we will get the same state of set and reset here. Okay, and then the block here is represented as D with a clocking. Okay, so the characteristic table of the D flip-flop is shown at the right. If the D is 0, our QT plus 1 is 0. And then if the D is 1, then QT will become 1. So thus, they retain the state of the value in the input. Okay, so this that's where they come out with the memory concept actually, because of the feedback. Okay, so now I have finished the chapter 3. Sorry, chapter 4 and chapter 5. Okay, chapter 4 and chapter 5. We have covered about the basic gates previously, universal gate, NOR and NAND, and then combinational logic and also sequential. Okay, so no lab for the sequential. It's just a theoretical that I have showed you before. And then if you can download the video, this is a video. You just click it and then they will show you the table. Okay, the table, truth table, and how does it works. Okay, how does it works. Okay, so is there any questions? Not a question for this slide, or maybe questions that you have done for the previous exercise that you want to ask. Question, do you have a question? Here is the this one. So this is the note for the sequential, the one that I have explained it to you. But we won't do the state diagram here, just because the drawing is quite complicated. So we just we decide that we won't do this. Okay, for next week. Okay, we won't do this this one next week. Okay, instead of I'll just explain it again for the JK flip flop and then D flip flop, especially the D flip flop. Because of the D flip-flop will be applied back again on the chapter processor. Okay, so that is the for chapter 6 for our lab. And then, yeah, is there any question for the lab 4? Next week, we will still continue with the lab 4 because of the question, this one, right? I didn't explain it yet about the question 4, question 5, then question 12, 13, 14. Okay, 14. Is there any question? Or maybe we can just maybe next lab. Okay, I will just look at the exercise that you have submit, and then let's discuss back again if there is some mistake that you made and then that needs to be rectified at that time. So, but then I did not explain it back to you yet, the other question. So that's why. So I want you to finish the question 1, question 2, and then go back and then do the rest of the questions. Okay, go back and then do the rest of the question, but you don't need to submit. Okay, you don't need to submit. Instead, this is an exercise for you. Can you do it on your own, and then maybe you want to check for the next lab, like that, because the answer have to wait until everyone has submit the lab assessment 4. Okay, and then question 7, 8 for the Kano map. Now you can draw this one. Question 9, 10, 11. Now you can draw it. Okay, because I have covered up the chapters about the universal logic and also about XOR. Okay, so this time we need to finish all these questions. Okay, but for the assessment, I'll just choose certain questions to be assessed. Okay, but the rest you can ask me during the lab. Another thing is that on Sunday, I would enable the quiz 1. Okay, quiz 1, which is chapter 1. I think so. Yeah. Chapter 1. Chapter 1 about computer system, right? Okay, so that would be your chapter 1. Maybe I will add. I'll just add number system. Okay. So quiz 1 would be chapter 1, introduction to computer, and chapter 2 and chapter 3, number system and number operation. Okay, so quiz 1. Alhamdulillah. Chapter 1 in until chapter 3. Okay, so do study. Please study. For the quiz, how many percent? 5%. And then what type of question? You just need to tick. Okay, multiple choice questions. Okay, multiple choice answer that you need to answer it within a certain times. 10 questions. 10 questions. Maybe 20 minutes. Okay, 10 questions, maybe 20 minutes. Only one attempt. So I want you to practice that. Okay, maybe for the second questions, I will give you a quiz that needs you to write, but that's for the purpose of practicing for your final. So those you never experienced about the final, right? So I'll give you the second test. Okay, so the second test or maybe the midterm test. The midterm test will be the same as the final test. So we need to practice how you need to answer that. Okay, so there's a certain process that you need to do. We will do the experiment, practical, how to answer questions. Okay, in final test or midterm test. Okay, so that one. Okay, so open date. Okay, date will be 20. Ni November. Astaghfirullahaladzim. Right. Okay, today is 29. 31 cannot I'll open it the whole day, so you can take time. You can take time to answer that. So 31 October. Okay, so 31 October, Sunday. Time open 9 until midnight 9 a.m. until 12 11:59 p.m. Okay, time open So quiz duration. Quiz duration is only 20 minutes. Okay? Now, you will be given 1 day to answer that quiz. Don't wait until the last moment to answer your questions. Just answer. Okay, just answer it. Okay, so don't wait. So that's all. I'll end the session here. Since you don't have a question, right? Okay, so no questions. I'll stop the recording. Okay.